Question 10.3, we still haven't completely finished, so let me go in here.
Yeah, it says it's due tomorrow.
Yeah, we're gonna change that.
Thank you, appreciate that.
We're gonna make that due April 7th,
Awesome.
because we have spring break next week. So it'll be due the Tuesday that we come back from spring break. Does that make sense? And right now I have 10.4 set to be due on that same night. We'll probably finish 10.4 on Friday,
Spring break, are we going, we're out the whole week, or is it just,
the whole week.
wow?
Yeah,
I don't think I remember the last time we had
no Mr. Reimer for a whole week.
No.
Don't know what you're gonna do.
I don't either. Don't worry, all right.
We'll get together in the math lab in the front, in the patio.
All right, let's finish up this 10.3. So, Monday we covered geometric sequences, right?
Yeah, infinite geometric sum.
Oh, I'm sorry, geometric series. There we go.
What number was it we had to only go 10.2?
Did I write on my face?
What number was it that we had problems on?
There's like three easy ones, like here.
Yeah, the one that.
So geometric series, the
we had the
limit
minus, or you get the
as n goes to infinity of s of n is a over 1 minus r.
You're right.
And this is on the condition that r is, absolute value of r is less than 1. A is the first term.
I already did it, but I just don't understand.
I'm hoping this pen will begin writing better. And R is the common ratio. So that's what we learned. Right now, we're going to talk about telescoping series. Telescoping series. And I believe we are still in 10.3. One moment. Uh-oh. Thought I had an example. I do. Here we go, this one. Let's start with this one. All right, telescoping series. Here's an example. We have a sum as k goes from 1 to infinity. Of 1 over k plus 1, in parentheses here, minus 1 over k plus 2. These are actually quite simple. Just like everything in math, they can be made difficult, but they're quite simple. So let's write out some terms for S sub n. Let's write out the first n terms. K starts out at 1, so if we put in 1 for k, this would be 1 over 1 plus 1, which is 1/2. minus 1 plus 2 is 3 1/3. There's the first term. Plus, next term, k is 2, put in 2 and we get 1 over 3 minus 1 over 4. Now k is 3, let's put in 3, and we'll get 1 over 4 plus 3 plus 2 is 5, 1 over 5.
Should be minus.
Minus, thank you. All right, then plus dot, dot, dot. So that pattern continues indefinitely. And the nth term will be 1 over n plus 1 minus 1 over n plus 2.
Is it?
Good morning. Are there any questions about what I just put on the board? Is that okay? Now look what happens here. Minus 1/3 plus 1/3. What does that amount to?
0.
0. So these subtract out. Minus 1/4 plus 1/4. Those subtract out. That is why it's called a telescoping series. It, goes out, comes back in, out, back in, kind of thing. That make sense? This minus 1/5 will cancel out with the positive 1/5 on the next term if we continued writing it. And all of these in between will be canceling out. The last term here will cancel with that one. Does that make sense? And now we are left with this 1/2 in the front that never canceled, minus 1 over n plus 2. That is the s sub nth term, 1/2 minus 1 over n plus 2. So that's the sum of the first n terms. So if you want to know the sum of the first 100 terms, we could put 100 in for n here and figure it out. That make sense? Well, this is an infinite sum. So we want to know the limit as n goes to infinity of s of n. We want to know the limit as n goes to infinity of this. Well, we just now found that s of n simplifies to this. So this equals the limit as n goes to infinity of that. 1 over 2 minus 1 over n plus 2. One over n plus 2. What's that approach as n increases infinitely?
0.
That approaches 0. So we have 1/2 minus 0, which is 1/2. The sum of this infinite sum, as we carry this out to infinity, is 1/2. Has a finite result. Does that make sense? And that is called a telescoping series. Let me hand out a paper. I apologize, I might have to we'll fix it as we go. It didn't photocopy very well. I don't know why. Maybe there's a toner in the photocopy machine. It's at the end. Series, which is what we studied on Monday. That's this. And so look across the top, you have series or test, geometric series. We're going to learn the divergence test maybe today. But anyway, geometric series, you have condition for convergence. The R, absolute value of R has to be less than one. So for one of these to converge, this must be true. Condition for divergence, if the absolute value of R is greater than or equal to one, then it diverges, it does not have a finite sum. Comments, if absolute value R is less than one, then the sum, that should be as K goes, that should be K equals 0 at the bottom and infinity on top. K equals 0 to infinity, A R to the K equals, and this is very important, you should have this formula, A over 1 minus R on the end there. Okay? You guys get that written in there? This A over 1 minus R, that's very important. If you look at this sheet, this is a list of tests, front and back. The geometric series and what we have on the board here, the telescoping series, there is no test for the telescoping series, there's just this process. Those are the only ones that we can find the infinite sum for. All the rest of these, front and back, are tests that only determine if it converges to a finite result or not. We'll be able to say whether it converges to a finite result or not, but we will not be able to say what that finite result is. Does that make sense? We will, in some cases, come up with ways to approximate it, but we won't. Some of these get very complicated and you can't come up with a method like this that actually tells us what it is. So anyway, I may have to, let me see what my originals look like. Maybe that's our printer. I may have to recopy this because this is bad quality. No, this is clear. It's the photocopy machine that did it. Maybe if I wait till after spring break, maybe they'll replace the toner and it'll look better. We'll see. Okay. All right. Let me give you one of these to do. This one will be, it'll look more complicated, but it's not.